So what I'm going to do today is, I've been asked to give a tutorial about device-independent random number generators. So I should just say, I know it's a very diverse audience, so I've pitched it at a level that will probably bore experts. So I apologize to experts in the audience, but yeah, it's supposed to be a tutorial, so I hope that's all right for you. I won't be offended if you walk out. Okay, so what am I going to cover? So I'm going to give a brief motivation as to why we might want to generate random numbers. Okay, you'll probably all have a good idea why we might want to do this. We're all doing cryptography, and the basic QKD protocol, of course, requires random numbers to implement it. Discuss what we actually mean by random numbers. So what are we actually trying to do when we say we'd like to generate a random number? What do we actually want from that? So I'm going to discuss some ways of generating them, starting away from device independence and leading up to device independent ways to do this. And then explain the main ideas behind device independent random number generators. So there's not going to be time, and it's not really the right place to give full proofs for that. And actually you'll see later this week, or even later today, some of these ideas taken forward in much more detail. Okay, then I'm going to also discuss what it means for a protocol to be secure. And finally, I'm going to finish by discussing a few related tasks. So these are going to be things like randomness amplification, which is slightly different from random number generation. Okay, so why are random numbers important? Well, here's just a few examples. Okay, I've mentioned cryptography already, but you can also think about gambling. So if you're a casino owner, you want to generate random numbers, and you don't want anyone else to be able to guess those in advance. You're going to make money anyway because you get to set the odds. So for you, it's just important that these things really are random. Okay, if they're perfectly random, you're going to win if you're the casino owner. But you're scared that when you try to generate your random numbers, maybe someone can guess them. And things like roulette, people with very, very fast cameras and some computational devices in their shoes actually sometimes can do better than you would like them to do. So that's an important motivation as well. And these are the kind of people that we might expect to start buying future quantum random number generators. Okay, and you also might want to use them in simulations. So a lot of simulations require randomness. You may think, well, in simulations, perhaps it's not so important to make the randomness secret. Okay, so we're talking about cryptography. We're going to look at random numbers being secret. You may think in simulations that part's not so important. However, what is important is that, or it could be important that the numbers are actually random. So what you might be worried about if you're simulating some process that requires random numbers is that actually, if your numbers aren't random, there will be some subtle correlations, and those could be affecting your simulation in a way that you just don't expect. Okay, so what we're trying to do, so imagine, the casino example is perhaps the easiest one to keep in your head. So you're Alice over there on the left, you want to generate some random numbers, and you basically want to make sure that no one else can predict them. So this kind of eavesdropper here over on the right is trying to predict these random numbers, and you want to make sure that can't happen. Okay, so ideally you'd like to go out there, you'd buy some machine from someone, some black box, or here it's a blue box, and this box should just spit out random numbers, x1, x2, and you'd like them to be completely unpredictable by anyone, and also uniformly distributed. Okay, so it's maybe not exactly clear what that means, so we could say this in a little bit of a more formal way. We can say, well, these bits that come out, these xj's, so we should talk about it with respect to some other random variable e, or later some other quantum system e, but for the moment take it to be a random variable. And we'd like that, so e is supposed to be representing kind of everything else. Okay, so we'd like our random numbers to be independent of everything else. So we'd like them in particular that when I condition on e, the distribution is 50-50, and that should continue, so the bits should also be independent of each other. Okay, so when I generate xj, I should include in E all the previous the previously generated bits. Okay, so that might be a classical definition, and of course later we're going to think about quantum adversaries. When we think about quantum adversaries, what we'd like is something more like this, that there's some quantum system, this A part that defines the output of the random number generator, and if this is in tensor product with Eve and uniform, then that would be an ideal random number generator. The fact that it's in tensor product means no matter what Eve does with her system, no matter how she measures it, it's not giving away any information about what's in this register A. Okay, so that's what we're aiming for here. So it's not just about this is the important point, it's not just about the outcomes having some uniform distribution, but also that they're actually uncorrelated with anybody else. Okay, so no one else can guess them. Okay, so what would we like from our protocol? So now, we know we've kind of said what a random number is. What do we want our protocol to do? Well, we'd like it to be secure. In other words, it actually is one of these random number generators. You can't guess the numbers. We'd like it to be reliable, so it should work well. If we use good quantum devices, it should not abort if there's no problems. We'd like it to be easy to implement, so yeah, as technologically feasible as possible, requiring few devices, and of course we'd like it to be as fast as it possibly can be. Okay, and in general these things will trade off against each other. So to make things more secure often means it's harder to implement and things like this. Okay, and also what we should get with when we go out and buy our random number generators, we should get a kind of statement of when it's okay to use it, or what is actually buying us. So it might come with a statement like this: if you run the protocol correctly, so if you use these devices in the way we prescribe, then no adversary should be able to learn the random numbers, even given unlimited time or resources. That would be maybe the most we might like to hope for, even unless physics is wrong, perhaps. You might have some caveats like this. Other random number generators might have some statement like this. So if the adversary is limited to having particular computational resources, then the random string can be treated as random for some certain period of time, or until some certain amount of the output has been used. So time-limited security, maybe it's just important to mention this because we often consider QKD, which is actually very closely related to random number generation. In QKD, time-limited security is actually pretty bad. Usually if I want to send a secret message, I don't want that secret to become unveiled even after a very long time sometimes. But for random numbers, it can be that you don't mind so much. So usually, if you take back this gambling scenario, if I can generate some random numbers to use in roulette, I'm going to actually reveal those random numbers pretty soon afterwards. So I might not worry if my random numbers are only secure for 20 seconds. So that's just an important caveat there. Okay, so how might we actually try to generate random numbers? So I'm going to explain several different ways that we might think about doing that leading up to the device-independent case. Okay, so I'd like to just explain, first of all, the scenario that we're always going to work in. Okay, so what we have is someone who wants to generate the random numbers, so it's going to be Alice, and Alice is sitting there inside this hashed area, and this hashed area represents a secure laboratory. Okay, so what it means is that Alice can control what goes in and out of this area. So in particular, the eavesdropper doesn't have any kind of cameras or something, or any ability to communicate or receive information from within the laboratory. Okay, so this is going to be an absolutely crucial assumption, and it's really necessary in order for us to do pretty much any cryptography. Okay, she's also going to have a trusted classical computer, so she can do classical computation, and she doesn't worry that someone's tampered with her classical device. Note that she should probably not connect her classical computer to the internet if she wants to really enforce this strong wall condition, or if she does, yeah, she should be extremely careful about what's going on there. And we also give a small random seed. Okay, so this is some initial source of randomness. Okay, so really often when we talk about random number generation, we actually really mean randomness expansion. So usually we need some random numbers to actually get started in order to generate hopefully more random numbers. Okay, so this is the generic setup, and in the classical case there's nothing else inside. Okay, so what do? What happens? We have random number generators. We can ask our computer to generate random numbers, and what's usually happening there is it's of course not well, it may not be a true random number, but usually it's some kind of pseudo-random number, and what a trusted classical computer can do is apply some function to my seed. Okay, so I should have maybe highlighted here, the eavesdropper always knows what the protocol is, so they always know what we're going to do. So in this case, the protocol is just some function, so what's going to happen is Alice is going to feed in this seed into her classical computer. It's going to output some function, which of course should be longer if we want to make more randomness. And we want to make sure that Eve, although she knows F, actually she can't really guess very much about this longer random output. Okay, so this is what happens in a pseudo-random number generator. Okay, first of all, you may think, well, look, Alice is now trapped inside this, her own laboratory. Nothing can get in or out. So, of course, if everything goes on inside this laboratory, then Eve will never know anything. And so, what's the problem? Well, of course, not only does Alice want to generate these set of random numbers, but she's probably going to want to use them later. Okay, so what you should imagine now is actually, okay, at the time of generation, maybe Eve can't really know anything about these random numbers, but now imagine Alice starts using these random numbers somehow. So, Eve goes to the casino, starts playing roulette. She sees the first few roulette wheel runs, and we still want to make sure that even after she's seen, some number of those, she still can't predict the rest. Okay, and that's going to be the problem with this kind of scheme in general. So because there's been a deterministic function, actually if you know the seed, you can know the output. So given enough instances of this output of F, you can in principle backwards compute the seed and eventually learn what the next sequence of random numbers are going to be. Okay, so if you have a very powerful eavesdropper, she could in principle do that. So in other words, if you know some part of there are subtle correlations in this supposedly random string, and if you know some part of the string, you can start to work out what those correlations actually are, and that will maybe help you then guess the next bits of the string. Okay, so this is the classical case, and the drawbacks are we can't have unconditional security, and in general we may not even be able to prove how hard it really is to break the protocol. But if Eve is not smart enough, then she won't necessarily be able to do this or work out these correlations, and then everything will be fine. Okay, but that's the drawback, and that's what we're trying to get away from with our quantum solution. So we'd like to actually not have to make an assumption about how smart the eavesdropper is, but we'd like to actually be able to prove security against an extremely smart eavesdropper. Okay, so now we move to the quantum case. Not much has changed except this little quantum device has appeared inside Alice's laboratory. So Alice now not only has all the same things as before, this random seed, this trusted classical computer, but now some quantum device to help her. And in the usual quantum case, so I'm not in the device-independent case yet, in the usual quantum case, the eavesdropper knows what this box is doing. So from the purposes of the security proof, she knows, or she can assume what this box is doing. Okay, so you may think, okay, well, what are we going to do? Well, why isn't this just as easy as using a beam splitter? So why can't we just generate random numbers? We create some photons, we send them through a beam splitter. If they come out one way, we'll call that 0. If they come out another way, we'll call that 1. Well, of course, you can do that. And this might be okay, and it is okay if you know exactly what your equipment's doing and you trust or you ensure that it doesn't change over time. Okay, so you may think, you've set up your beam splitter correctly, you've got your two detectors, but maybe actually something's happening to them, maybe the temperature's changing, they're wobbling a bit, maybe actually, in principle, you should really check what they're doing every time. But yeah, in principle, this might be okay. And there's one other thing that we're also assuming is that we're also trusting the physics, and a more subtle point, even that the physics is complete. Okay, so you probably all, you know that according to quantum mechanics, if I send photons through a beam splitter, half of them go one way and half of them go the other way, and there's no way to predict which way it is. But you might like to ask yourself, why do you really believe that? So how do you really know that there really is no way to actually predict those? Okay, and that's part of the motivation for device independence. So how, from a given process, why do you really believe that it's doing something random? Okay, and so ideally we'd like instead to have some certificate that the outputs actually are random. Okay, so the trusted quantum case, it does allow us to remove some of the classical drawbacks. In particular, we can have security based on our understanding or our best understanding of physics. It's slightly harder to implement, but probably not too bad. And our security is going to rely on the devices behaving correctly. Okay, so there's the quantum case. Actually, although there's a random seed available there, we didn't really use it for this beam splitter type protocol. Okay, so now moving to the device-independent case. So here's the setup for the device-independent case. What's happened? Well, I've now given Alice two devices because, well, at least two are going to be needed in this case. The devices now have this little red devil on them. So what that means is that they're untrusted. And because they're untrusted, I've wrapped them all in their own little extra secure laboratory space. Okay, so in particular, we want to make sure these devices can't talk to each other, in particular during the protocol. So they've been enclosed in their own little sub-laboratory. Okay, so we've got this random string, and in the case of randomness generation or expansion, what we want to do is generate a longer random string. Okay, I just want to maybe just make a small comment here. So, we have these two devices. We're going to do something with them. There's a bit of a difference with QKD. So in QKD, we also often need multiple devices, but in QKD, we have these two devices in separate laboratories, and these separate laboratories, the people in them, usually Alice and Bob, need to talk to each other, and Eve can listen to that. Okay, in randomness generation, everything's enclosed. You can think of these devices, you can call these devices Alice and Bob, but both Alice and Bob, in a way, are inside one big laboratory, and so we don't have to worry about an eavesdropper overhearing any communication we need between these devices. So that's just a slight difference there to maybe how you're used to thinking about QKD. Okay, so we don't want to make any assumptions about the workings of the devices, but we are going to need, or we do use some assumptions, namely the strong lab wall assumption and the assumption that there is some initial randomness. Okay, so this is the important point. It's not really randomness generation, it's really randomness expansion. Okay, and the point is although there are some assumptions, we can move those away from the devices. Okay, so this is where the word device, or the term device independence comes from. Okay, so I want to talk now about security proofs. So a security proof should be a mathematical statement. It should say, here's your protocol, here's the assumptions you're making, and if those assumptions are correct, then your protocol will be secure. This is what a security proof should tell us. I'm going to discuss later a little bit how to formulate these, but this is just the idea. And so really the security proof takes place in somewhere that I'm calling here theory world. Okay, so what it means is that under some precise mathematical assumptions, some precisely specified protocol will really generate secure random numbers, for example. But of course, where our protocol really takes place is actually the real world. So we're actually we've got some assumptions which, let's say in some kind of quantum protocol, we might assume that we can generate a perfect single photon, for example, but then we go out to our lab, we've got to actually try to do that. If our device isn't behaving exactly as we modeled it in our security proof, there's a possible mismatch. Okay, so it could be that our security proof, because we assume too much, it's not actually really relevant for our real-world protocol. Okay, and that can be a problem. It's maybe more of a problem in the case of QKD, but even in the case of randomness generation, or any kind of protocol, this is a problem. So you prove security in this very nice enclosed mathematical framework, and then you say, well, because of that, now my real device in the lab is actually or this real protocol that I'm running is secure, but if the way I've modeled the devices in my security proof doesn't really match how they're actually behaving in the real world, then there's no reason that my security proof is correct anymore. Okay, and so this is, in a way, another way to motivate device independence. So what we'd like to do is make weaker assumptions, and the weaker assumptions that we can make, the more security we get. So the less I have to assume about my devices, the more likely it is that my real devices are going to satisfy those assumptions. Okay, and device independence is in a way the limit of that, where I don't want to make any assumptions about the devices. Okay, so this should remove the mismatch problem, at least at the level of the devices, between the real world and the theory world. Okay, but there can still be mismatch problems, of course. So I've still got these other assumptions, like the strong wall assumption. If the strong wall assumption fails, then things can still break down. Okay, so it's not true that by just assuming nothing about the devices, I'm going to guarantee that everything works perfectly, but at least I don't have to worry about the physics of those devices. I do still have to worry about how strong my lab walls are, or that there's no double agents or something like this inside my lab. Okay, and one thing to say, or this is just a way you can think about it, because I'm not really making any assumption about how the devices are operating, it means actually that I can think about it as, well, these devices may have even been maliciously constructed. Okay, so you may think, well, I don't necessarily believe that they've been maliciously constructed, but if you don't want to make any assumptions about them, in effect, you're allowing for that. Okay, so you can think about it like the eavesdropper. I mean, when thinking about how to attack a given protocol, it's maybe helpful. You can think about it's actually the eavesdropper who's created my devices. They've done so in the most cunning way possible to try to break my protocol. Okay, but maybe some of the real advantages are that your protocol remains secure even if your devices stop working properly or if they're tampered with. So maybe you don't think, you don't want to make the assumption that your eavesdropper has really built your devices. Maybe you built them, but maybe someone's come in and tampered with them. Maybe they've stopped working in the way you thought they will. In a device-independent protocol, the working of the device is in a way detected on the fly. So as you run the protocol, it's also checking that the device is working sufficiently well, and if it's not, it will just abort. Okay, so it's not true that we can always generate randomness even with very bad devices, but if our devices become bad, then our protocol should abort. That's what's supposed to happen. Okay, so because we don't trust these devices now, or we don't want to make any assumptions about them, the protocol is going to have to test them. So, initially, when you first start thinking about device independence, you probably think, well, without assuming anything about the devices, how can I hope to do anything? But actually, well, of course, the way you can do something is by having some way to test what these devices are doing. And the question is, well, without making any assumptions, how can we actually now enforce some constraints on what these devices are doing? And the way to do that is, of course, to do some test on them. Okay, so let's now just think a little bit about how can we how can we test some device? So you go out there, you buy a random number generator, or something that someone claims is a random number generator, this box, and you take it home. You don't know what's going on inside it, but the person claims it generates random numbers. Now you can ask, well, okay, how can I really try to verify that claim? Okay, so according to, remember this beam splitter example, according to quantum mechanics, it's generating random numbers. How can I really know that that's happening? Well, what you can try to do is take some long sequence of outputs and try to see if they somehow look random. Okay, so you can see if roughly 50% of them are 0 and 50% of them are 1. Okay, that's not a very sophisticated test, but there are actually some very sophisticated tests. Here's a few that I stole from Wikipedia. So these are, I mean, it's not too important exactly what these are, but these are some of the ways that people use to test outputs of random number generators. So you basically know some properties of random sequences, and you check that your random number generator satisfies those properties. Okay, so while these tests, of course, they may expose a poor random source. Okay, so if your random number generator isn't very good, you may be able to detect that using these tests. But actually what I want to claim is that these can never test for true randomness. Okay, and remember that to claim that something is really random, I want to make sure that it's independent of any other system. Okay, so that no one else can actually guess the outcome. So although these tests, in a way, are checking for the uniform distribution property, they can't test whether the outcome is random, in the sense that no one else can guess it. Okay, so the claim is there's no good test that acts only on the outputs. So there's no function f such that if I apply that function to a sequence of outputs, it will output, and this function outputs either accept or reject. It will accept only if the sequence is random. Okay, and the way you can very easily see this is, well, suppose there is some true random number generator, and inside your random number generation factory, this true random number generator, so that's the kind of light blue one, actually is used to generate some true random numbers, and these true random numbers are just fed into your actual random number generators that you go out and sell. Okay, so these y1, y2, they're the true random numbers. So if they really are true random numbers and the randomness tests are good, then then f of y1, y2 will output accept, at least with very high probability. So what happens inside the factory is those random numbers are generated. They will output accept to any test, but they're put inside this darker blue box, which is the one that's actually sold. And that darker blue box is just programmed to output, its outputs xi are just equal to the yi. So it just holds in this random string and just gives the outputs. So of course this will also output accept. It behaves exactly as the y's did, but this is not obviously now going to be really random in the sense that we want. In particular, anyone working in the factory can know these random numbers. Okay, and that's exactly what we want to avoid. Okay, so there's no test that works only on the outputs of a random number generator that can check that there's randomness in the sense that we'd like. Okay, well, that's okay, no test on the output. What about if we test on the input and the output? Okay, so here's a more advanced test. So we're not going to just take outputs from this device, but we're going to get a device that also requires some inputs. Okay, so now we need some function that acts on the inputs. Remember, we've got some random string, some trusted random seed string to make the inputs. And we'd like to now do some test on both the inputs and the outputs that outputs either pass or fail. Okay, remember always, the adversary is going to know what this test is. Okay, and they can supply some pre-programmed classical device that will always pass this test. Okay, so the idea is that for any sequence of inputs, they can program their device to give a particular set of outputs such that it will always pass. And so now the outputs, although they do depend on the input, they're not really new randomness. They're actually deterministic function again of the inputs in such a way that this will always pass. Okay, so actually not only is there no test that only acts on the outputs, there's also no test no good test that works with only one device. Okay, so we've kind of said, well, okay, it's looking quite hard to do this test now, but actually, if you have two devices or more, you can actually do a test. Okay, so what we actually need to do, and this is how pretty much all device-independent protocols need to work, is they need to demonstrate some Bell inequality violation. Okay, so as far as I know, the only way, if you really don't trust what your devices are doing, the only way you can put a hard constraint on them is to ensure that they violate a Bell inequality. And of course, if you want that to be a real constraint, they should do that in a loophole-free way. Okay, so the main idea is that, well, if we can, and remember what we're trying to do is generate randomness. So we'd like to make sure that these devices can't behave in a deterministic classical way. And if we can ensure that they violate a Bell inequality, then what that ensures is that there is no classical behavior. And in particular, this will allow us to generate randomness. Okay, so this is really the idea behind, and not just actually behind device-independent randomness generation, but in particular behind device-independent randomness generation. Okay, so we buy these two devices. We better make sure, we need this loophole-free violation, so we have to make sure that these devices don't talk to each other. Okay, so I've drawn this like solid lines down the middle here. This is representing actually that if you remember my slide before, I put each of these devices in its own strong lab. So this is representing that wall, which basically is there to prevent the devices from communicating with each other. Okay, and then what we say is, well, if we now take these devices and start testing them, if the output distribution, this P of xy given AB, violates a Bell inequality, and if the inputs A and B are random, and if the devices cannot communicate, then according to Bell's theorem, X cannot be known by any other party. And furthermore, X is also not a function of A. Okay, so this is if they violate a Bell inequality, then we can, by this argument from Bell's theorem, we can know that that we can use them to generate randomness. Okay, so note that although I've got this strong wall separating the devices, both devices are really in one laboratory. Okay, as we saw earlier. Okay, and this is true no matter how the devices operate. Okay, so no extra assumptions are needed here. We didn't have to assume anything about the physics of the device, just provided that the devices cannot communicate. Okay, so, that's gone a bit small, don't worry. Okay, but notice that this doesn't mean that X is perfectly random. Okay, so what we'd like to do is generate perfectly random outcomes. The fact that we've violated this Bell inequality just means that Eve cannot know X perfectly, but of course we want more than that. We're not very happy if we generate random numbers, but an eavesdropper can guess them most of the time, but just not all the time. We really want them to be perfectly unguessable. So, okay, we're going to have to do a little bit more about that. Okay, and so I've mentioned, okay, we need to violate a Bell inequality. As an example, I just want to use CHSH. Okay, so this is a standard Bell inequality. It's the simplest one to describe. So the Bell inequality you might think about is the probability of winning a CHSH game. Okay, so what happens there? Well, each of the devices should be given one of two possible inputs. I've just labeled them here. So the first device takes inputs either 0 or 2, the second device either 1 or 3, and the devices should give binary outcomes. Okay, and in the CHSH game, probably almost everyone knows this, but just to get the notation. So if X is equal to Y, for these three combinations, we're going to call that a win. And for the final combination, A, B is 0, 3, we're going to say they win if the outputs are different. Okay, and the probabilities of winning the game depend on what kind of physics is going on. In particular, classical physics allows the game to be won with probability up to 3/4, and in quantum mechanics we can increase that to roughly 85%. Okay, so you may be used to seeing, well, the Bell value of 2, and this has got a Bell value of 2 root 2. That's an exactly equivalent statement, just rather than using probability of winning, it just uses some other measure of how the game's going. Okay, and in particular, in order to achieve this 85% winning probability in the quantum case, what actually has to happen is that both those devices have to share a maximally entangled state. Okay, so they have to share a state of the form given here, and I've just drawn on this diagram an illustration of what measurements are needed. Okay, so it's not going to be too important, but the 0 means Alice is going to measure in the 0-1 basis, 2 means she's going to measure in the plus-minus basis, and Bob's measurements take these intermediate bases. So if you think of this circle as like a plane of the Bloch sphere, then these are intermediate bases in between, and this is the way to get to 85%. Okay, and the crucial thing is that in order to do so, we need this maximally entangled state. Okay, so this now allows us to start to formulate, or to think about formulating a way to use a Bell inequality to generate random numbers. Okay, so you can now think about an argument like this. Well, if these devices maximally violate a Bell inequality, then the devices must share this maximally entangled pure state. Okay, what that means, therefore, is that they're maximally entangled by a monogamy of entanglement. There can't be any entanglement with Eve. Okay, so the total state of the whole system looks like this psi AB, that's the state shared by the devices, and then it's tensor sum phi E. So anything the eavesdropper holds is completely product. Therefore, Eve has no information about the outcomes, and X will be uniform. And if that's the case, then the outcomes basically are already for us random numbers. Okay, so that's a kind of sketch root of the kind of statements that we might want to make. But actually, that's a little bit too easy, because what happens in practice is we don't perfectly violate our Bell inequality. Maybe we get some near maximal violation, or maybe we just get some small violation. So we'd like to make all these statements robust in principle. So this might mean that the devices, we don't necessarily know they share a maximally entangled state, but they should now share some state that's somehow close to maximally entangled. And that means everything's almost unentangled with Eve. Eve has now almost no information. X is almost uniform, blah, blah, blah. And then at the end, so we're not going to, before we just said the outcomes can be used as random numbers, but now they're going to need some processing actually to get random numbers. Okay, and actually the way I've described this proof here is not really the best way to do it. It's actually very hard to do the proof like this, but we don't need to actually make such a lot of statements. In particular, we can kind of take a shortcut and just go like this. So usually we're not that interested in what the state is. We don't necessarily need to care about whether the state's really close to maximally entangled, or we don't need to make really some precise statement about that. All we need to do really is to go from the input-output behavior of the devices straight to some statement about how random the outcomes are. Okay, so this first slide is kind of morally why it should work, but then actually the kind of statement you directly want to prove is more like this. Okay, so just as an illustration, I just want to try to give a short illustration of how we can connect the Bell violation with Eve's knowledge. Okay, so here's a set of correlations that suppose we've done some experiments, or for whatever reason we're convinced that our pair of devices is behaving according to this. Okay, so here's a conditional probability distribution of the joint outputs given the two inputs. Okay, so each entry in this table is a P of xy given AB, a joint conditional probability distribution, and I've labeled it for each of the possible inputs and outputs for each party. Okay, so epsilon is some number that we've actually measured. I don't want to say exactly, well, it doesn't really matter exactly what it is, but you can see also that the probability of winning the game here, if these really are the correlations, is 1 minus 2 epsilon. And there's a value of epsilon for which the perfect, or the quantum correlations I described before, based on the measurements I mentioned on maximally entangled states will actually look exactly like this. So if you make measurements on maximally entangled states using the measurements I said, there's a value of epsilon such that this is the correct table. But actually our observations might not have that epsilon. We might not have our devices working absolutely perfectly. Okay, so the question we want to know is, we've gone out there, we've made these observations, how much can we know about X? Say Alice's output. How much can an eavesdropper know about X? Okay, so remember that Eve, the eavesdropper, has constructed these devices, so she's programmed them to do something, and what actually she can do is try to decompose them in a convex combination of quantum realizable distributions. Okay, so if the eavesdropper is limited by quantum mechanics, then each time she can basically pick some z, and instead of sending a device that behaves exactly like this, she can send another device that behaves as p of xy given abz, or given ab for each z. So it's like she's actually sending a different device, but she knows or she's actually sending devices that do something a bit differently, but she knows what they're doing. Okay, and because the observed distribution is a convex combination, when Alice does her test, she can't tell that this is happening. Okay, so this is a way to think about what Eve can try to do. Okay, and actually, so that if Eve is quantum limited, she should make sure that the distribution she sends a quantum. It's actually, just for the sake of this argument, I want to assume that Eve's a bit more powerful and she can actually send any no signaling distribution, just because it's much easier to tell whether a distribution is no signaling than to tell whether it's quantum. And this is just an illustration of the ideas at the moment. Okay, so what Eve should now do is then take this table that's displayed up there, and she should try and decompose it in such a way that she knows as much as possible about the outcome. Okay, so here's a decomposition that Eve can do if she's limited by no signaling. So with probability 1 minus 4 epsilon, she prepares this distribution on the left, which is actually a non-local box distribution. So this always wins the CHSH game. We can't actually build this quantum mechanically, but suppose for the moment that we could build this. Okay, and then with probability epsilon, she sends one of these 4 things. Okay, and notice for these, X is always known perfectly. Okay. So overall, what can happen here is that a no signaling Eve can now guess X with the following probability. So there are 4 of these that occur with probability epsilon. If one of those is sent, Eve can always guess X correctly. So that contributes 4 epsilon to the probability. But for the first one, there's a 50-50 distribution on every single X. So with probability 1 minus 4 epsilon, she sent that, and then she has to just guess. And so this is the overall guessing probability. Okay, so that just shows roughly or gives an illustration that the Bell violation really can be connected to how much information the eavesdropper can know. Okay, but this is of course a very simple case. I've just imagined that I've already know what the distribution is. The protocol's actually got to also try to establish that. So one of the main difficulties of the full proof is to bring this all together and really get to this final guessing probability. Okay, so now I want to just discuss some of the basics behind these protocols, or what the main ideas that go into an actual protocol is in a bit more detail. So first of all, so we're going to do all these tests. Okay, so I discussed that we have to do some tests on both devices. So what's going to actually happen in the protocol is somehow Alice is going to choose a bunch of random inputs, A1, A2, A3, and also B1, B2, B3, and she's going to make those inputs to her devices. And she's going to take the outputs. Now, we've seen that if these devices can win the CHSH game too well, then she can hope that the outputs are random. But actually, remember what we're trying to do here is we want to actually expand randomness. So one of the problems is that doing these tests is actually going to cost us randomness. Okay, so in particular, this test that we've looked at before requires A and B to be one bit of randomness, okay, and at best it could only hope to give, so it requires 2 bits of randomness, and at best it could only hope to give 2 bits of randomness out. There's only 2 binary outcomes anyway. But we want to actually make more randomness, so this is going to be a bit of an annoying test, because it's going to, if we just keep doing this test, it's going to chew up our randomness. Okay, so what actually usually happens in a protocol is that instead of, we don't just test every time, but what we do is we divide into some test rounds and some generation rounds, and the test rounds are only going to be a very small subset of the time. Okay, so we have our devices. Most of the time we're just going to feed them some fixed inputs, and every so often, and not that often, we're going to decide to test those devices, and when we do the tests, we're going to make sure that they violate a Bell inequality. Okay, and the idea is that because we're going to choose where to do these test rounds at random, the eavesdropper has to basically stay honest the whole time. Okay, so here's an example of just what's happening. So a G is a generation round and a T is a test round. So most of the rounds are G rounds, but there are some test rounds thrown in. For the test rounds, Alice and Bob always make some fixed input. And on the, for the generation rounds, they always make some fixed input. For the test rounds, they're going to use their initial random string to do this and collect all the outputs. Okay, so on the T rounds, at the end, all the outputs are going to be collected, and we're going to make sure that the value of, or the probability of winning the CHSH game is sufficiently high. Okay, and if it's too low, then the protocol will just abort. Okay, but if it's high enough, we still have to do a little bit more. Okay, so I said earlier that just because we can show that there's some randomness doesn't mean that there's absolutely nothing that a possible eavesdropper can know. So violating a Bell inequality shows that there must be some randomness, but we want more than that. We want perfect randomness. And so what we actually have to do is then take the output and do some post-processing to it, apply a randomness extractor, and that should now distill us out a final key and get rid of any possible information that the adversary has. Okay, and I just want to note that to do randomness extraction, we also require a short random seed. Okay, so luckily we've got this, necessarily we have this randomness at the beginning, and we're going to need some of that randomness to also choose the extractor to do. Okay, and one of the key difficulties in the security proof is working out actually how much randomness we can get out. Okay, so and what we have to do here is take Alice's string. This randomness extractor will basically compress that, and we have to decide how much compression we can actually get away with. And one of the difficult things is to actually work that out. Okay, so I'm not going to describe processes or how to do that, but I think you'll hear more about that later on today. Okay, so we can think about this protocol now as acting a bit like a filter. If we want there to be a significant probability of the protocol not aborting, then it's basically filtering out devices that have a small Bell inequality violation. Okay, so if there's a large Bell inequality violation, it implies it's difficult for Eve to guess, and if Eve can't guess the output very well, then we can compress the string using an extractor. Okay, so these are the ingredients that we need. Okay, and then of course we want to make sure that we get more randomness out than we put in, so we should do a little bit of randomness accounting. Okay, so where do we use randomness in this protocol, or this type of protocol? Well, we need it to choose the test rounds, and on the test rounds we need it to choose exactly which tests to do. Okay, and then we also need it to seed the randomness extractor. Okay, but the point is, because we're doing the test rounds very rarely, the fact that we need 2 bits per test is not really a problem. So we actually don't need a lot of randomness to, first of all, choose the test rounds. We're almost always not going to do a test round, so we don't need much randomness to choose the test rounds. And Therefore, the amount of randomness consumed for doing the tests is not very high. And also there are very efficient extractors, so we also can get away without using much randomness there. Okay, and for the output, well, if everything goes well and our devices are operating pretty well, then we can get roughly 1 bit out per round. That's the idea. Okay, and therefore overall we can get expansion. Okay, so now I just want to move on to thinking about the security definition. So what does it actually mean for the protocol to be secure? Okay, so this is a typical way we can try to define security. It's based on defining an ideal functionality and comparing how well that ideal functionality can be distinguished from the real protocol. Okay, so we can imagine that Alice has some way to make perfect random numbers. Okay, but she's not going to necessarily use that way. She's either going to use that way or she's going to run the real protocol. Okay, and if there's no way to distinguish whether she's running the real protocol or using this other way, then we can say that the protocol is secure. That's going to be the idea, and this is what happens in composable security proofs. Okay, and why do we want this? Well, let me just discuss a little bit about composable security. So we want to do some randomness expansion. Presumably we're going to want to use that randomness somehow. So here's a generic thing that's happening. So there's some larger protocol, it's got some steps. So at some step n, we're asked to call our randomness expansion subprotocol, okay, and then somewhere later we're probably going to use this randomness somehow. Okay, and you can imagine that at this step where we're asked to call our randomness expansion subprotocol, either Alice is going to use the real protocol or she's going to use the ideal protocol. Okay, and we're going to say that the real protocol is secure if no one else can tell the difference. Okay, so for a particular larger protocol, can you tell whether if I substitute this step n for the real protocol or the ideal, can you actually tell the difference? Okay, and then we'd like to optimize that over all possible larger protocols. Okay, and if we still in the worst case larger protocol, we still can't tell the difference, then we can say that we have security. Okay, so here's what's actually going to happen in the case of randomness generation. So Alice in her lab is going to run either the real protocol or the ideal. What now the distinguisher can do is supply some states and devices. So imagine there's some other player now who's trying to tell whether the real protocol or the ideal is going to happen. So they can supply the states and the devices, and they can also hear the output. So they can hear the whole string of the output. They can also hear if the output aborts. Okay, so we imagine we do the protocol, and then the output, Alice just shouts out whatever the output of the protocol is. What we can't hear, or what the distinguisher can't hear, is anything that goes on inside any little steps inside the protocol. So inside Alice's laboratory, she can't tell what randomness was used for the inputs and so on, but she can hear the output of the entire protocol. Okay, and even in this case, we'd still like it to be virtually impossible to tell the difference. Okay, so to do this, we need to actually define what the ideal protocol is, or what we'd like the ideal protocol to do. Okay, well, remember right at the beginning, or a lot earlier, I said, well, this is, in a quantum case, what we'd like the final state to look like. Okay, so if Alice and Eve have a shared state like this, then we can say that this is a good key. Okay, so you might think, well, why don't we just define the ideal to be a device that just outputs this? So it gives the A part of the system to Alice and the E to Eve, and that's the ideal. However, we don't simply define the ideal in this way, and the reason is it will be very easy to distinguish it from the real protocol. Okay, so remember in the real protocol, the distinguisher gets to supply some states. The distinguisher can always supply dud states. If the distinguisher supplies dud states, then the protocol is very likely to abort. But if the ideal protocol says just give the output according to this, it will never abort, and now we can actually distinguish very easily. Okay, so actually we have to define the ideal in a slightly different way. And what we can do is we can just take the real protocol and modify it such that if it does not abort, right at the end, Alice replaces her output by this perfect key. Okay, so you can imagine Alice has some hypothetical device that can just give her an output according to this state. So what Alice does in the ideal protocol is she just runs the real protocol. If it doesn't abort, she throws away whatever she's got and she just takes her output from this device. Okay, this prevents distinguishing by looking at abort. Okay, so with the ideal defined in this way, the ideal and the real protocol both abort in exactly the same conditions. It's clear there's no way to distinguish by the probability of aborting. So now the distinguisher can only distinguish in the following way. So first, the protocol had better not abort. If the protocol aborts, then there's no hope. And if the actual output of the real protocol, so that's, I've called this row AE here, if that can be distinguished from the output of an ideal random number generation protocol. Okay, and so this is actually the condition that we need, and to distinguish two quantum states, we usually have the trace distance is the mathematical quantity that defines that. Okay, so this is the condition usually that we would, or this is the kind of statement that we'd like to prove in order to show that we have security. So how much time do I have? Sorry, 13. 13, thanks. Okay, so what the security statement says is something, it's a bound on the a priori probability that both the protocol does not abort and the output can be distinguished from perfect key over all possible devices. Okay, so what it says is that before you run the protocol, I can make this statement that no matter what devices you've been given, there will be only some very small, well, hopefully it's very small, but probability that both the protocol will not abort and the output can be distinguished from perfect key. Okay, and I just want to make an important caveat, so we don't make statements of this form. I mean, often maybe we say this, but we shouldn't, it's not really precisely what we prove. So it's kind of tempting to say, well, given the protocol did not abort, the key is secure, perhaps, except with some small probability. But actually, it's worth noting that we can't really make statements of that form. And the reason is as follows. So suppose that the states supplied are actually classical. Okay, so they've got there's no quantumness in them, they're just giving some deterministic outputs. Okay, we're going to run the CHSH game many times. Now, it's not impossible that actually we win every time. Okay, it's extremely unlikely, but it's not impossible. But nevertheless, so if we take this protocol, or we take these states, we run the protocol many, many times, eventually we will actually pass the protocol. But there's nothing, we haven't generated any randomness, there's no randomness inside. So conditioned on the protocol not aborting, it doesn't mean that there's necessarily, that we've generated secure randomness. Okay, so this is just an important kind of conceptual point about what it means to prove security. The statement really is, before we ran the protocol, the probability that both it does not abort and the output can be distinguished is small. Okay, so that statement is correct, whereas the second type of statement is not correct. Okay, so now let me just talk about a couple of technological aspects. So, okay, I haven't presented a proof, and I'm not going to, but I've presented the ideas behind a proof, and you can work these through and develop a full security proof. So we have these now, some theoretical proofs for device-independent randomness generation. Okay, what about in practice? Okay, so what do we actually need to do? Okay, and as we've seen, the key ingredient is a Bell inequality violation. And what we need to do is, of course, close the detection loophole. So later this week, we're going to see a lot of talks about some very tricky experimental work that shows actually we can do loophole-free Bell violations. In fact, for the point of view of randomness generation, that's a little bit overkill because we don't need to close while we need to close the detection loophole, it's not so important for randomness generation to close the locality loophole. Okay, so in fact, doing this completely loophole-free Bell experiment is not necessary, and actually, for generating randomness is not necessary. And if you want to generate randomness, the only thing you need to worry about really is the detection loophole. Okay, so what the detection loophole says is, or if you don't close the detection loophole, what it says is, so we're going to actually use these devices. A real device will sometimes not make an output. Okay, it will somehow, you'll ask it to make an output, but it will somehow have lost the quantum state, or something will go wrong, and it will not make an output sometimes. So in the detection loophole, we imagine that the device exploits that in order to make us think that we've violated a Bell inequality when actually we haven't. Okay, so we need to make sure that's not happening. A malicious device should not be able to trick us into thinking that we've violated a Bell inequality when we in fact haven't. And so it's important for us to close the detection loophole. Okay, so in order to make sure we've done that, we should really include in our statistics the failure events and take those into account as well. Okay, but I just want to make a note that it's easier to do this for randomness generation than for QKD. And the reason is that QKD, we have Alice and Bob, they're in separate laboratories, and they probably want to be fairly far apart. Closing the detection loophole gets much, much more difficult with distance. But for randomness generation, the two devices really can be fairly close together. They should be far enough apart that we can shield them in a reasonable way, but they should be reasonably close together. Okay, but there's no real need to close the locality loophole, although of course it doesn't hurt if you can close this as well. So let me just justify that. So what is the locality loophole? Well, the locality loophole says, well, the reason you appear to violate Bell inequality is because your devices weren't space-like separated, and so actually, you made this input A to your first device, but that was able to be communicated to the second device before you made the input there. And if the second device knows both A and B, it can easily behave in a deterministic way to generate Y, and then we haven't verified anything quantum there. Okay, so that's what the locality loophole suggests. That's a way out of believing that you violated a Bell inequality or that something quantum is going on. Why don't you need to close that? Well, first of all, you do need to make sure that the devices can't do this. Okay, but we don't have to ensure that by space-like separation. That's really the point I'm trying to make. And the reason not is, well, it goes right back to the scenario I discussed at the beginning. We have this strong lab wall, but we can also put our individual devices inside their own kind of lab walls. We can make sure that they don't communicate just by assumption. Okay, so if you can close the locality loophole by space-like separation, great, but if that's too difficult, because we anyway have to assume that we have some way to prevent communication from inside the laboratory, we might as well put that same assumption between the devices and just assume they can't communicate with each other anyway. Okay, so if my lab wall is not secure, if I don't have any way to make a secure lab wall, I'm not going to be able to do any useful random number generation anyway, because I can imagine that, or at least not with an untrusted device, because my untrusted device could just communicate everything. All my new random numbers could just be communicated directly to an adversary. Okay, so I'm going to have to make that assumption about my overall lab, so I might as well also enclose my individual devices in that. Okay, so actually the important thing really is to have a good way to close the detection loop. Okay, and we also would like these things to be fast. Okay, so this is something that I think is now a new aspect, that if we'd like to be able to close the detection loophole, and we'd like to be able to do these Bell experiments in a fast enough way, and in particular fast really means to compete with current approaches. Okay, so if this isn't, if we can't compete on the rates with current approaches, we can at least compete by saying, we actually get a better guarantee of security than current approaches. Okay, but ideally it would be nice to do both. Okay, so I'm coming near the end now. I haven't given very many references so far, so I thought, I should at least give some. Probably there's a lot of work on this. There are probably some things that are still missing, so apologies to people who are missed out. So, okay, thanks. Just wanted to mention, so this is further reading if you're interested in this. So the first, work on this is my PhD thesis from 2007, where I started developing some of the ideas behind this. There are no security proofs there. These were developed later, and this Peronio paper, PM is Peronio and Massar, and there's a paper by Fairgales and Schaffner. So these developed security proofs against classical adversaries. Okay, after that, I think this paper of Vazirani Vidic is probably the first protocol that developed security against quantum adversaries. However, it still was not able to tolerate any reasonable level of noise. That came in this later few papers by Carl Miller, who's here, and Yao-Yun Shi. So they first showed that actually noise can be tolerated, and later today you'll hear a talk by Rotem who will explain actually that a much better way or that a lot more noise can be tolerated than was first seen. Okay, and there's also this Coudron and Yuen paper, this CY, which shows another slightly interesting result, that actually we can generate an arbitrary amount of output randomness. So you may also, what we're trying to do is take a small random seed and generate a longer output. You could ask, well, how much output can I generate? They showed actually that an unlimited amount of output can be generated. Okay, so just in the last couple of minutes, I just wanted to mention another task which is very related to randomness expansion, called randomness amplification. So in randomness amplification, so maybe one of the sort of embarrassing things slightly about random number generation is that we need random numbers before we can get started. And unfortunately that's necessary. However, perhaps we can, in the spirit of doing device independence and trying to weaken assumptions, perhaps we can make the assumptions about that weaker too. Okay, so in the case of randomness expansion, we have this perfect random seed. In randomness amplification, we say, well, suppose that seed isn't perfect. So suppose instead it's replaced by this box, this epsilon box, and that generates random numbers, but they're not necessarily perfect random numbers. They may be somehow partly correlated with some other system, and we nevertheless want to generate perfect randomness. So in this scenario, we have this box, and we don't make an assumption that it's perfectly random, but there's still some randomness inside it, and we'd like to use our devices to make perfect randomness. Okay, so that's a slightly different task of randomness expansion. So randomness expansion, we have perfect randomness, we want to make more of it. Here we have imperfect randomness, and we'd like to make it perfect. Okay, and one way, maybe I should skip this actually, I think I'm running out of time, but there are different ways to describe the source and use that. Okay, and there are just a few references on that. Let me skip that. Okay, one other thing we might also think about doing is, and actually randomness amplification can work in this scenario too. We may also ask, in the spirit of removing assumptions, maybe we could try no longer assuming that our devices are quantum. Okay, so maybe it's interesting I mentioned this when I gave this little sketch argument, but perhaps if the devices are not quantum, we can nevertheless still generate randomness. Okay, so just come to the summary. So the main thing is that this kind of thing on the right, that the fewer assumptions we can make, the more security we have. Okay, and this is the whole motivation behind device independence. If we can base our security proofs on weaker and weaker assumptions, then the more likely it is that our real devices will satisfy those assumptions, and therefore the more secure our outputs will be. Okay, so the classical protocols for randomness generation may allow us to give some time-limited security. Okay, standard quantum protocols like this beam splitter will allow this to be upgraded to unconditional security, but yeah, nevertheless, we have to trust what our devices are doing. And these device-independent protocols, they will allow us security against even device failure or tampering. Okay, and so the advantages are they certify security on the fly, so any calibration errors or anything like this is automatically caught. The protocol should just abort. And some of the open challenges are, well, we'd like to increase the speed of these things. Yeah, there's another open problem, which is sensible ways to reuse untrusted devices. I haven't really talked about that. And can no signaling adversaries be? No. I think there's something missing there. Can they? Can no signaling adversaries also be treated in the proofs? Okay, that's all. Thank you.
Okay, so we have left time for questions for the speaker.
I think this non-signaling condition or these walls are quite a strong assumption. Is it possible to replace that with a kind of epsilon wall?
Sorry, the no signaling assumption on what?
I mean, the assumption that the walls you introduced, so that you have this protection around your devices. It's a quite strong assumption that no information can leak out or in. Is it possible to replace that by kind of an epsilon wall or something?
Okay,
like
yeah,
this?
this is a good question. So this is another way you might try to weaken the assumption. So we have this remaining assumption that the lab walls are strong, or that the walls around our devices are strong. Now, if the devices can leak outside the laboratory very slowly, then if you wait long enough, they'll be able to get all the information out that they want. So I think even if there's any channel with non-zero rate from within inside the laboratory to outside, if you wait long enough, you'll eventually be able to exploit that channel to get all of the information out. So I think it's actually not, well, yeah, one can ask about rates. So you could say, you know, maybe if I just need security for a certain amount of time, provided my channel can't be whatever channel this leak channel is, provided there's not enough time for it to leak the amount of information I want, then maybe you could do something like this. But because eventually this information can all get out, it's not such a nice assumption to weaken for this reason.
A little related to the previous question, if you have those two untrusted devices in your trusted lab, unless they've got pre-stored entanglement, like a quantum memory, they need to have a quantum channel between them. And so you have to worry about also making sure that that's not used for nasty purposes.
Yes, absolutely, yes. Fortunately, you can, in a way, do that because you can make sure your device does not know its input until it's received the quantum state, or the quantum state is inside its little sub-laboratory. But yes, you may worry about this.
Well, they can remember from the previous time. I guess that's the reusing question. Yes.
Well, you don't want to give your devices all of their inputs at the same time. If you give them sequentially, this can help break this kind of attack.
You mentioned that you need some randomness to keep running the protocol.
Or to start the protocol.
Only to start it, not to run it afterwards?
Well, you're expanding randomness, so...
Because I wanted to ask that, like, for instance, you choose which rounds to check and all that stuff. So if you use randomness from previous rounds, you incur the risk of introducing correlations and stuff and around?
If I reuse...
If you use randomness that is happening for previous rounds.
Right, so this, okay, so what we assume is we've got some initial random string, and we use that to generate some longer string. So, and now you can ask, can I reuse okay, now I've got my longer string, can I reuse that to make it even longer, something like this? Yeah, so this was tackled in this paper of Kudron and Yuen that I mentioned. So they show that if you do the protocol in the right way, you can actually do that. But you have to be very careful about this. So it's not just the case that you can feed it back in. You have to actually check some additional conditions. Because the device can remember everything that happened before.
Use the other microphone. We can't hear what is being asked. Can we use the other microphone? If you are using the microphone. Not me. I couldn't hear the previous two. Okay, yeah. Is there a question back here?
So I hope that works now. So if you have a regular random number generator and you need your random seed only for randomness extraction, how bad is it if your seed is not perfect?
Okay, yeah, this is, it depends in what way it's not perfect, I guess. So you don't want to, I mean, one thing that's very important is that your seed is independent of your, the randomness that you're trying to extract from. So in this sense, yeah, I mean, this is something that you would like. Whether it should be uniformly random, I think is not so important, but I'm not totally sure about this actually. Yeah, there are probably some more experts in the audience.
Other questions? Okay, please thank the speaker again.